Hello everyone. So today we're continuing our topic of operational amplifiers and their application as linear amplifiers. We're going to look at op-amp circuits that are used as a difference amplifier and the op-amp circuits that are used as current sources. So the first linear amplifier that we're going to look at today is a difference amplifier. This op-amp circuit amplifies the difference between signal V2 and voltage signal V1. So we're going to use the golden rule, first and second golden rules of op-amps to analyze this circuit and find an expression that relates V out to V1 and V2. So first rule, using the first rule, I have IN equals to IP, that's equal to 0. And second golden rule, I have VN is almost equal to VP, that's okay. So this is the second golden rule is because of the presence of negative feedback. That is, there's a feedback network that connects the output node to the inverting terminal at the input side of op-amp. So I'm going to use the node voltage analysis method and write the node voltage equations at an inverting terminal or VN node. So I'm going to write VN minus V1 divided by R1 plus Vn minus V out divided by Rf is equal to 0. Also at node P, I have Vp minus V2 divided by R2 plus Vp divided by R3 is equal to 0. Because Vn and Vp are almost equal, then I have that equal to R3 divided by R2 plus R3 multiplied by V2. Substituting for Vn in the first equation, I can get V out is equal to negative Rf divided by R1 multiplied by V1 plus 1 plus Rf over R1 multiplied by R3 divided by R2 plus R3 multiplied by V2. So I can further simplify this equation if I choose the values of R3 over R2. I choose the values of resistors such that R3 over R2 is equal to Rf over R1. If I choose these resistors such that the ratios are equal, the ratio of R3 over R2 is equal to Rf over R1, and then I have V out is equal to Rf over R1 multiplied by V2 minus V1. So this amplifier circuit amplifies the difference between node voltage V2 and node voltage V1. So let's look at the second application of op-amps as a transconductance amplifier. So in this amplifier, the output is current, the current that flows through the load, this IL, and my input is VI, voltage that's applied to the positive terminal of op-amp. So I would like to show that that the value of the output current is independent of the value of load resistance. So it acts like a current source, and it can be and I can change the value of IL by changing the value of VI. So first and second golden rule again. So IN is equal to IP. That's an ideal op-amp. That's equal to 0. Second rule, Vn is almost equal to Vp because again I have a negative feedback here and the output is connected to the inverting terminal of input through a resistive network. So from there I have Vn equal to Vi. So this Vn node voltage at the inverting node or input terminal of op-amp is equal to Vi. From there I can write the node voltage equation at this node. Vi over R1 is equal to IL. So the current that flows through R1 is equal to the current that goes into this node, into node of Vn, and then from there IL over Vi is going to be equal to 1 over R1. So the value of this current IL output is independent of the value of RL load resistor. We just showed that, and I can set the gain of this transconductance amplifier by choosing different values for R1. So the problem with this current source is that the load is not grounded here, and this might not be desirable in some cases. We're going to see next another op-amp circuit configuration that's used as a current source, and in that current source the load is, or RL is, grounded.